Whenever you're ready.
Fantastic, thanks. Okay, so I am Ben McKeon. I'm a final year student of Maths and Physics here at UL, and I am going to just tell you a little bit about modeling the orbit of the International Space Station using symplectic integrators in Python. So I suppose to begin with, what are symplectic integrators, and I suppose in a way to describe them simply while also kind of getting into a little bit of the underlying mathematics. They're basically to do with what we have here is what's called the Hamiltonian, which is in essence a fancy way of describing the energy of the system. So this is the kinetic energy and this is the potential. So then what we find is if we were to plot this in RV space, which is essentially a diagram where we plot R versus V, you see that it's not immediately obvious, but there is this function here working away in the background. And basically at every point in space, for a different value of R and V, you have two different vectors that will be plotted in two different directions. And then these form a parallelogram. And this parallelogram is referred to as a linear symplectic structure. Then if we solve Hamilton's equations for this system, which basically involves differentiating this Hamiltonian equation here with respect to V and then again with respect to R, we generate what's called a phase flow, which maps the initial point of the trajectory to some other point at a later stage in time. And then for this flow, the Jacobian, which kind of describes the derivatives of this system, is related to the flow by the relation. And basically what this quantity here basically describes the area of that parallelogram that is mapped out by the two vectors at an instance in time. So by applying the flow to those vectors, we see that the area of the parallelogram does not change with time, and it is said to be conserved, that the linear symplectic structure is conserved. And that leads us to this condition, which says that a phase space function is symplectic if and only if it satisfies this relationship here. And symplectic methods, they don't specifically conserve energy, but the energy drifts much more slowly when it's calculated using a symplectic integrator rather than one that it does not satisfy this equation here. So I suppose the next question would be, why should we use them? And particularly in orbital mechanics problems. And I suppose the main reason for that is the fact that while they don't conserve energy necessarily, they're very useful at keeping the errors that occur over a long time scale. Say if you wanted to send a probe to maybe Mars, like we saw last month with the Perseverance rover, you'd want to make sure that the errors are very, very small because the margin for error there is absolutely tiny. And then unfortunately, we see things tend to go wrong if we make errors, say, like as in the Mars Climate Orbiter here, which I use as an example, used imperial units instead of metric. And while that was the main cause, the algorithm that they used further compounded the errors so that we see that one tiny slip is all it takes for a mission to go completely wrong. And symplectic integrators tend to resolve this issue. And we need methods that are accurate, stable, and fast. And because they preserve the area of that parallelogram in phase space, this translates to an error-free method when we look at it more realistically. So what I have here is a plot of the actual orbit of the ISS using what's called the SGP4 model, which is the simple general perturbation model. And it's kind of considered the industry gold standard for plotting orbits and trajectories. And I've let that go for about one orbit corresponding to the station's position on the 28th of April, 2008. And basically what this uses is what's called a two-line element set, which is a bunch of different designations which correspond to different spacecraft. So this can be used to track almost any satellite in orbit, but I specified it towards the ISS. And then if we want to model the orbit using a different method, say, these are the equations that we have to use, where basically this is derived from, Newton's law of universal gravitation, and these were the initial conditions which were derived from that two-line element set. So if we begin with the velocity of Rayleigh method here, which is a numerical method, and it's quite popular because it tends to work quite well in describing systems such as orbital mechanics, but it's also applied to other instances such as in particle accelerators and other physics issues. So what we have here is this describes the position as it evolves in time, and this describes the velocity and h here is the time step. So if we try to update the position and the velocity, say every 5 seconds, which is what I did, and using the same initial conditions on the previous slide, we get the following result, which looks virtually identical to the SGP4 model. So we're thinking, okay, this looks pretty good. But if we look at it in 2D, we see that once the Earth is kind of taken out of the way and we look at it top down and we zoom in, we see that it tends to spiral outwards by about 25 meters over the course of 6 orbits. But on the scale of the distance at which the ISS orbits, this is virtually negligible. So it looks good at first glance, but I suppose the main question we could ask is, could we do any better? And the answer to that question is yes, I suppose, because what happens in reality is that the ISS tends to spiral inwards rather than outwards due to atmospheric drag. And we need a method that accounts for that without having to modify the governing equations and take, I suppose, fluid mechanics and other nasty effects into account. So I suppose further questions we could ask are, do multiple methods exist and how do we find the best one? So if we start with what's called the implicit midpoint method here, which describes how the position and velocity update in time as follows. And if we notice that Vn+1 occurs in both equations, we can sub the second equation into the first to get one long equation for the position. And we see that xn+1 appears on both sides of the equation. So we have to use a tool such as the fsolve function in Python to solve for x1 at each time step. And this can prove quite computationally expensive. It can take a long time to do and it can move quite slowly. But unfortunately, we see that while we do get the correct behavior spiraling inwards, it tends to do so quite quickly, actually. And unfortunately, this is dangerous if you're trying to describe how the ISS moves, and it's completely inaccurate. It moves inwards by 1.2 by 10 to the 6 meters. So that means within 2 orbits, the ISS would completely decay. So instead, we look at a better method called the Chin-Chen-4A method, which is quite complicated, I suppose. But if we're to basically simplify that down to the result it produces without having to get into the nitty-gritty here of the implicit differentiation of the equations, because SciPy, a library within Python, greatly assists with this task, we see that the orbit looks much better. Obviously, it doesn't decay by as much. And then we see there just by a small bit. But once again, looking at it in 2D, we get a better idea of how it decays. And it decays by 1.5 by 10 to the 5 meters over the course of 6 full periods, which is less than the amount by which the implicit midpoint decays over a single period. And then I suppose it's not perfect either, because it takes 16.28 methods to fully decay. So it's an improvement, but we're not fully there yet when it comes to symplectic methods. So then, by comparison, if we use a non-symplectic method, we see that the RK45 method, which is included in the SciPy library, and it's kind of included as a generic kind of tool to solve equations such as this, and we see that it uses the Dorman-Prince technique using 4th and 5th order Runge-Kutta methods, which are fairly generic solvers, and it kind of compares the two of them as a means of finding the error. And using a variable step size, it is able to decide itself which is the best time step rather than using the fixed 5-second step size that I used. But unfortunately, we see that this performs very, very poorly, as almost within 1 orbit, the trajectory has almost completely decayed. And obviously, like we discussed earlier with the Mars mission, that this method is obviously, unfortunately, not suitable for this problem. Again, looking at it in 2D, we see that it decays by 1.5 by 10 to the 6 meters over the course of 8 periods, excuse me. And again, this is not suitable for orbital mechanics, as it would take just over 2 periods for the whole orbit to completely decay. So finally, we see that symplectic integrators tend to outperform their non-symplectic counterparts when applied to orbital mechanics problems. And again, I used a 5-second time step, but if we used maybe a fraction of a second, maybe 0.01 seconds, we would produce more accurate solutions, though this could end up being more computationally expensive. However, to solve the problem of computational expense, we could use a compiled language such as Fortran, C, or Julia, which would allow computations to be done much more quickly. And the same analysis could also be applied to highly eccentric orbits, such as comets or trajectories, maybe Halley's Comet or something like that, which only comes around every 60 to 70 years. So thanks very much for listening, and I will take any questions if you have them.